Hello everyone. In this video we are going to talk about how to use CalcPlot3D to visualize the 3D regions over which we do triple integrals. So, we're not going to be able to see the mass part of things if you're integrating some density function, but we are going to be able to see the region that defines our, three bounds, right? If we're doing like dx, dy, dz, something like that. So in this video, we'll talk about rectangular coordinates, and then in the next video, I'll talk about how to deal with like spherical and cylindrical coordinates. So I'm actually going to go to uh, our book here, Active Calculus, and we're going to start with number 13 here and just see this solid and how to view this, basically recreate this picture in CalcPlot3D. So mostly because if they don't give it to you, like in some future problems down here, you see it's just a whole bunch of words. How can you make a picture yourself, right? So for this one, we're bounded down below by y equals x squared, and then z equals 0, so that's giving us the xy plane, and then up above our top shelf here is z equals 1 minus y. And so we can go back to the region part like we're doing with double integrals and stuff like that. And so we have to first figure out what this looks like down in the 2D realm. So here, if we're looking 2D, we have the parabola y equals x squared, but this is actually our lower bound, right? Because if we go upwards in the y direction, we actually peak at 1 here. So if you use the default and it's y equals stuff, then we're actually going from y equals x squared to y equals 1. And then our functions, we were going from z equals 0 to z equals 1 minus y. So I've already got z equals 0, and then I can make this 1 minus y. Click. And there we go, right? So we see our parabolic region that's kind of cut off, right, at 1. And then over here, we see exactly what we saw on our active calculus book. So this is what you can do. If you want to see something like a little bit more complicated or how you might work through a specific problem, we can look at number 15 here. So I think this is kind of a cool thing to do. So we've got two paraboloids, and the first thing that we're asked to do here, because basically we have a top and bottom function, and you could simply plug in a few values or graph them yourself in CalcPlot3D to figure out what's on top. So let's actually go ahead and do that. So I've gone ahead and just added function z equals f of x, y to create both of these. Now you can see here that they just kind of look the same. I can't tell which one's which, so I'm going to color code them. So we'll make this one red, and the other one, I'll just make that light blue just to get a contrast. So this tells me, I should probably make it transparent so we can actually see what's going on here. Okay, so the one that is below is the light one, which is z equals x squared plus y squared. And then the red one is on top for our actual region, right? And so they intersect here, and then the red goes on top and the blue goes down beneath. The rest of the part is kind of outside of their intersection, so that's all we would care about. And this is going to be relevant for later, but we're trying to figure out where they intersect. And so you can see that it's going to be some sort of circle, and if you look closely, it looks like it's somewhere around 1.5 for the radius, and we're actually going to find out that it's exactly radius of root 2, which is about 1.4. So I'm going to first go over here and just already put in, I want to start with my bottom as x squared plus y squared, not equals, plus y squared. And then this 8 minus 3 times x squared minus 3y squared. So that I know, but then I have to figure out my region down below, right? So that's what I was kind of trying to do here. It's going to be some sort of circle. So the book tells us we should eliminate the variable z and determine the curve of intersection, and then sketch it in the xy plane. So how you figure out intersection is you just set them equal to each other. And so if you just move the x squared and y squareds over, right, you're going to get 4x squared plus 4y squared equals 8. Divide by 4 throughout everything, and you'll get x squared plus y squared equals 2. And that's exactly your your circle of radius 2. So this is where you could then solve, for instance, if you wanted to solve for y, right? Y is then plus or minus the square root of 2 minus x squared. And so if I want to create this circular region here, I can do negative the square root of 2 minus x squared, positive square root 2 minus x squared, and then my x to get the whole circle is going to be negative square root of 2 to positive square root of 2. And so you can see your circular region goes just below 1.5 in terms of its radius, and we can actually see, maybe it helps to again zoom out a little bit, but you can see this paraboloid down below, and then this one coming down, and then this is that circle of intersection. If you don't like this little nasty piece here, and you can kind of see these like missing edges, that just comes from the grid lines. You could add more grid lines and do like 45 and 45 or something, and it tightens it up a little bit. You could do a few more and like actually close it off completely, but this is probably enough to figure out what's going on. Okay, so hopefully that helps visualize these regions and see how you can translate equations that maybe start out with just z to figure out what your region of intersection looks like and how you might solve for that so that you can input specific y bounds or x bounds, right? So here we did y equals, you could just as easily do x equals f of y, and you could do the left as negative square root of 2 minus y squared, and your right as positive square root of 2 minus y squared, right? Just solving for x rather than y, and then this would still be a negative square root of 2 to square root of 2, and we'll get the same circle, right? So either way works, and this should help you visualize regions that you're integrating over when you're doing triple integrals, anytime you're doing dx, dy, dz, or some variation thereof. All right, that's all I've got.